So what on earth could Dr. Mather have done to deserve such praise from one of the most important and famous scientists of the last century? The answer is that he discovered the thermal origin of the cosmic microwave background, proving beyond a doubt that it had an origin in a hot, dense early universe, essentially proving the Big Bang. He was also the first to show that the cosmic microwave background has small anisotropies, which are the origin of structure. And what do I mean by structure? I mean stars, galaxies, and perhaps more importantly, all of us. We are the end product of these remarkable anisotropies in the early universe, which Dr. Mather discovered. Now, I think most of us would probably have been tempted to sit on our laurels at this point and say, I've contributed a lot, time for someone else, but not Dr. Mather. He went on to become the project scientist for a little satellite you may have heard of called the James Webb Space Telescope, the most sophisticated telescope ever built, now at a Lagrange point and doing truly remarkable science. So I believe Dr. Mather is going to tell us a bit about that. And currently he's moved on from the position as project scientist to become a senior astrophysicist at NASA. And we are truly very lucky to have him. So please join me in welcoming Dr. Mather.
Well, thank you, Asa, for that lovely introduction. And it's always a good time to remind people that nobody ever does these things themselves alone. There are teams and teams and teams of people. In fact, here on the front picture of my story, I have a picture of the James Webb Space Telescope, and point out that it took 20,000 people, mostly engineers and technicians, to actually build it and fly it, along with many, many scientists, managers, bookkeepers, lawyers, and every other possible specialty that it might take to put something complicated up into space. So there it is. The project I will tell you about there is a joint project of NASA with the European and Canadian space agencies. And by the way, anybody in the world can use it. You just have to send us a proposal when we ask for proposals. Now, to tell the truth, most of us don't win every time we propose, but anyway, we try anyway. So are people hearing me well in the back?
Yes, sir.
Okay, thanks. So it's working. So now try the clicker to try the next picture. So it was mentioned that we did this thing called the Cosmic Background Explorer, a COBE satellite. It got us a Nobel Prize. This is what it looked like. At least we imagine it this way because, of course, this is artist drawings. In the center, you see a helium cryostat carried two instruments that operated at 1.4 degrees Kelvin. And those were for two purposes. One was to measure the cosmic microwave background spectrum to see if it really has the black body spectrum that is predicted by the expanding universe story, which basically says the early universe was so hot and dense that it couldn't be anything else but a perfect black body spectrum, and then the expansion preserved that. There's another instrument in there to look for the cosmic infrared background that was accumulated from all of the galaxies that formed afterwards, and that measured something, and it said actually there's twice as much light as we thought there would be, and it's not fully explained yet. Around that central tank is a collection of 3 boxes containing microwave receivers, and those were used to measure the cosmic anisotropy, the hot and cold spots. So here is my thesis project grown up. A prototype of this was my thesis project at UC California, Berkeley, and it was conceived by Paul Richards, my thesis advisor, and we built it and launched it on a high-altitude balloon, and it went up and it did not work. I got to write a thesis about a non-working project, but we had faith that it would work, and the next time it flew it did, but I got to write the thesis up, and I thought in the back of my mind, well, this is pretty hard, and I'll probably give up on this, but if I ever get a chance, it would be good to do it in space. So I got a job at NASA in New York City to become a radio astronomer, working with Pat Thaddeus, who studied those things, is gone now, but anyway, 6 months after I got there, NASA said, we want proposals for new satellite missions. I said, boss, my thesis project failed. We should try it in outer space. Being not short of nerve at the time, and too young to know how hard things really were, but it went up and it did work, and it did indeed confirm the spectrum isn't exactly the same as a black body. And how did we know? We had a simulator for the universe. Thing up there in the corner called movable black calibrator, it's a black body. It's an effectively perfect radiator of something that should match exactly the spectrum that comes in from the sky, and it did. So it didn't take very long to say, we got it. And there's what we got. After just 9 minutes of good data, we were able to make that plot. So pointing out that inventing optics makes you a discoverer of something new sometimes. So there was a competing theory, by the way, called the steady state theory, and nobody that advocated that theory ever was able to make a prediction that matched this. They couldn't do it. So they didn't give up, they died. So got a standing ovation for this chart when I showed it to a couple of thousand astronomers on a Saturday afternoon in Washington, D.C. in January of 1996. So, my golly, 1990, slipped my digits. So, a few years later, a couple of years later, this was the map that Stephen Hawking liked so much. It is a map showing the universe as it was young, when it was about 400,000 years old. And we use that date because that's when the temperature of the universe had cooled down enough that the material became transparent. Ordinary gas-like air that you can see through. Before that, it was a plasma full of loose electrons, and the loose electrons were able to stop the light from propagating. So when the universe became transparent, the light was free to move in our direction and in every other direction. So this is our snapshot of how it looks now. But we say that's what it was like when it was quite young. So those hot and cold spots, why are they so important to Stephen Hawking? Well, number one, if there were no spots, if the early universe were not slightly different from place to place, there would be no reason for one spot to accumulate more matter than another. So galaxies would never have formed. We would not be here if there were no spots. Number two, most of those spots come from something we call cosmic dark matter, which is deduced and never observed. It is completely transparent. We call it dark, but we should call it transparent. And number three, the pattern is affected by cosmic dark energy, which is causing the universe to expand more and more rapidly now. We don't know why that is either, and we can't see that either, but at any rate, this pattern tells us that information. So that's why it was so important to Stephen Hawking. And by the way, if we ever do find out what made the spots happen in the first place, maybe we'll have a test of quantum gravity if there is ever such a theory. People have been hunting for such a theory a long time, and we don't have it yet. But don't give up. Somebody here, maybe a graduate student, will become a professor, will become a discoverer, and we'll have that Nobel Prize. So, got to go visit the king of Sweden and get my diploma, and I showed my chart a lot. So, parties and speeches, that's what we have since then. And by the way, I got some money and I started spending it on students mostly. Some ballet students, because my wife was a ballet teacher, and some summer interns at NASA Goddard to encourage them to come back, which many have. So what are we going to know? How else do we know about the early universe? Well, the Hubble telescope was launched in April of '90, just a few months after the COBE satellite was launched, and it's still working beautifully. Why is that? Because astronauts went up to improve it and fix it 5 times. And we're not currently planning to do that again. The next plan is we have to make sure that it doesn't hit somebody when it gets old. So we either have to boost it way up or head it for the Pacific Ocean. I don't know what will happen. But anyway, we cannot bring it home safely and put it in the museum. I'm sorry. It's too heavy. So anyway, it's beautiful. It took a lot of pictures, and I guess you may remember that when it was launched, it was out of focus. It was a complete disaster. NASA was the butt of jokes all over the world. How can you have such a wonderful thing and it be so completely messed up? So, well, anyway, we did fix it, which meant we found out the error, and the company that made the error got sued, and they paid a little bit, but nothing like the cost of recovery. And the astronauts went up with new equipment, and it's in great focus now and still working beautifully. So what else happened? Well, astronomers started taking pictures with it, and they said, by the way, we thought we were going to see the formation of the first galaxies because this Hubble telescope was so much more powerful than anything we ever had before, but it can't see far enough. So they wrote a book and they said, please build us another telescope that's even more powerful and we'll pick up infrared light. And we'll tell you more about that. But anyway, it does. And so here is the Webb telescope design to go along with that picture I showed you at the beginning. It is a thing called a 3-mirror anastigmat telescope, which is to say it's a fancy version of a Cassegrain telescope, which is to say it's got a big, almost parabolic mirror that collects the starlight, convex secondary light that reflects it down into the instrument package, and in this case there's a third mirror that improves the optical performance. So the special thing about this one is this telescope has to fold up for launch because it's bigger than the rocket. The aperture is 6.5 meters, the rocket's 5 meters inside diameter, so a little folding going to go on here. So those 18 hexagons that you see making up the big hexagon are all adjustable on little motors. And very, very clever engineers made that possible. By the way, the mirrors are made of beryllium. You might say, why beryllium? Well, it's extremely light, it's extremely stiff, and the metallurgists have been doing their job for a long time, so they've got a recipe where you can make this stuff cool down to a low temperature and not twist and distort too much. So it'll keep its shape. So that means you can polish up the mirrors at room temperature, cool them down, and have them be the right shape when they're cold, after you account for all of this. So we have to go through a cycle. We polish them up, cool them down, measure them, warm them up, polish off the extra bumps that we measured before, cool them down, and the next time they're right. So huge, huge accomplishment for the engineering teams that learn how to polish beryllium. By the way, beryllium's bad stuff for you. If there's a powder beryllium and it gets into your lungs, you can become very sick. So all of that process is done inside hermetically sealed milling machines, and every particle of beryllium is captured and sent back to the factory. So huge, huge, huge technical accomplishment, but it's what it takes to do this project. You say, well, why did you have to use beryllium? Well, we had lots of ideas about other things, so we had 12 contracts to other companies that said, we've got another idea, but only one was successful. So that's why it's beryllium, why it's made out of gold-coated hexagons. The gold is for infrared reflection. So there it is, and it works beautifully. So what have we got on board with it to be able to detect all the wonderful things we're telling you about? We have 4 instruments, cameras and spectrometers that cover the entire wavelength range from 0.6 microns to 28 microns, and a very general purpose, because nobody can say we're designing something to answer one question. We're going to need everything. And besides this, it might be used, as it turns out, 50 years after people started. So you have to be pretty generic in what you're going to offer. So there it is. We have instruments from Canada, United States, and Europe, and they cover everything we could imagine doing that we could also afford. So some pretty special things in there. In particular, we have a spectrometer that can observe 100 different galaxies at one time by opening up little windows to let them in. At Christmas time, a lot of us have this thing called Advent calendars, and the little windows open up so the saints can look out. Well, we have a controlled version of that with 250,000 little windows that we can control by remote commands from the ground and let the galaxies in. So all of them work, and we're very happy about that. So here it is. This is our scary movie, Unfolding It in Outer Space. I used to show this in advance, and people said, why are you showing that? That's too scary. This is, well, it's a wonderful challenge, and now that we know that it succeeded, you could say, well, how did you make it work? Well, number one, this unfolding process that you're seeing was practiced in the lab 4 times. And by the time we got to the 4th round, we say, we think we believe it. We better not test it again, because what if we screw up on the test? We don't want to wreck it doing a test. How else do you do it? Well, you have teams of people who are paid to be grouchy to tell you all the mistakes you might be making. So please write them down and check them all out. So these are called review committees. And if you are ever blessed with a large project, please do have review committees. You might not like it, but you will need it. And it will be so much better to feel bad for a few days than to feel bad for a lifetime. So do not hesitate to get the advice of people who complain about your work. It's probably good advice for all of life, isn't it? Just don't take it too personally. Okay, so there's the telescope. It's all unfolded in outer space, and it's extremely complex. And you say, isn't that amazing? And isn't there a cheaper and better way to do it? And the answer is no. If you want to get this information, you have to build this telescope. So there it is. At this point, it's been unfolded, but it's still not ready to use because it hasn't been focused yet. Anyway, that's the telescope. And how well does it work? Well, this is an optical diagram. It shows how close is the surface of the mirror to being perfect. And on the left side, you see what it was like when we built it. The mirrors were all built up, and the small deviations from the average gray color tells you there's a bump or a valley in the mirror. And it's pretty darn good. And on the right side, you see there's one with a bump on it in the lower right corner that had everybody worried. And what does that mean? It means a little sand grain from outer space hit the mirror at something like 30 kilometers a second. Sand grain that's so small you could barely feel it if you had it in your fingers. But it would really hurt if it hit you at 30 kilometers a second. So we were pretty worried because we didn't plan for that kind of event. We knew there would be many such events, but we thought they wouldn't be making such a big bump. So we do actually get about one bump a month, but most of them you can't see because they're so small. It's just we had this one big one, and we're worried, but we're lucky. We've been working now for almost 2 years, and this is the only one. So we're feeling more lucky than we were. So we are now expecting a lifetime of about 20 years from today. So very happy about that. So why do we get 20 years, by the way? What sets the lifetime of this observatory? It's got little rocket jets on it that are used to maintain the orbit, to keep it in the proper orbit, which is orbiting around the Lagrange point 2, 1 million miles from Earth. And also we need it to deal with the solar torque. Sunshine pushes on that big sunshade and tries to turn the telescope over if it's not perfectly balanced. So every now and then we have to fire the jets to get rid of angular momentum. Anyway, skipping over all the details of how we did it to show you what we got. Here is our first data release from July 11th of last year. Joe Biden issued this at the White House. And we see a picture that has three main things you can notice. One is some stars with this six spikes sticking out. Those are ordinary stars nearby, and the spikes are due to diffraction of light around the edges of the hexagons. So completely expected and exactly as we planned. So there are more than three in there, but you have to look more closely. Second big thing you see is right in the middle is a big fuzzy white thing, which is a gigantic galaxy that we knew about already. It's actually the center of a cluster of very, very, very massive galaxies. And we knew that would be there, and we knew also that some of these little pink arcs would be there. The pink arcs are magnified images of even more distant galaxies. So when Einstein worked out his theory of relativity, general relativity, he said gravity works by bending space-time. That means it can focus light. And that means the giant galaxies in the middle, the big white fuzzy balls, have enough gravity to magnify and distort the images of more distant clouds out there. So these funny looking arcs, the pink ones, let's see if I can get my laser to work. These, many of them come in pairs. Some of them are very distorted. Anyway, there are dozens of them in this picture that are highly magnified images of much, much, much more distant galaxies. So we are really super thrilled with this because it gives us the use of nature's extra lenses in our telescope. So it is so spectacular. I think I have a picture of a big surprise in here for us. Well, here's one of those galaxies that's in there. We call it the sparkler galaxy because it's got these things called globular clusters. Each of those little white dots there is a cluster of stars. We have them here in our own galaxy. They're roughly 100,000 stars together in a group. And here we are seeing them when the universe was very, very, very young, 9 billion years ago. And galaxies themselves were young. So now we're beginning to ask the question, well, which came first, the galaxy or the globular clusters? So that's part of our job, is to figure out the history of galaxies. Did they sort of form all at once, or did they form from little pieces? So here's a sign that at least some of them are forming with little pieces very early on. I guess I didn't include my picture, but we have one picture that we took in this same area, which shows an individual single star from an immense distance. Has been magnified like 10,000 times. So we can recognize it out of all of those thousands and billions of other stars out there, because it just happens to be lined up exactly on the place where the magnification is so high. So I thought that was possible, but I never thought we'd see it. And we do see it. We see it quite often. So here's another pretty picture for you. This is a laboratory for understanding star formation. The little galaxy in the upper left went right straight through the middle of the big one. And what we're seeing is a splash. So it pushed a lot of gas straight out from the center of the big galaxy, and it initiated star formation in that splash. So all around that ring and all that bright stuff in the right-hand galaxy is brand new stars that were just formed by the impact of the one gas cloud hitting another. So we sort of understand the generic nature of formation of stars. The details, we need help. So this is a place to look. This is a place that's another spiral galaxy. It looked like a very ordinary one, and now you see it's got holes in it. This is like a slice through a sponge. So in a sponge, why are there holes in a sponge? I mean a synthetic sponge. It's because gas pressure was in there when the material was being turned into a sponge. So where's the gas pressure coming from that makes this galaxy have holes in it, like this one? What we think is there was a burst of brand new stars that burned a hole right here when the stars are new and young, and they're very, very bright, very hot, and they push material away. So there's one. There are quite a few of these holes in the galaxies. So now we know this is sort of normal and typical in other galaxies, and it's a way to study the effect of star formation after the fact. So now we see the new stars are being born around the rim of this hole. This is a Webb telescope version of the Pillars of Creation picture that we got with Hubble. And you can see, well, number one, it's kind of obvious. There's the wind blowing from the top right to the lower left, pushing the material around, stripping off the surface, and causing things to happen. So when the wind blows, it compresses the gas that's inside there and causes new stars to be born because of the compression. So why does a star get born? A star gets born when the gravity of a cloud of gas is able to overcome the pressure of that same cloud of gas. So a little extra kick from a blast wave coming through space can start a whole new generation of stars to be born right there as we speak. So also, by the way, the infrared capability that we have lets us see inside the dust clouds. So why is that? Light's a wave. It means that when light encounters an obstacle, if the size of the wavelength is larger than the object, then the wave can just go right around the object and reassemble itself. If the wavelength is small compared to the object, then it looks more like just an object and the light bounces off. So we are able to see inside these clouds because we're using infrared light. And so we can see much farther in than we ever could before. And the longer the wavelength of light that we can use, the better. So you see, in particular, up in the upper right-hand corner, we see a brand new object being formed, and the red light shows something's burning bright and hot. So another star formation laboratory for us. Here is a new star being born as we speak. This thing that looks like a hamburger bun is actually got a star right in the middle of the hamburger. And you cannot see the star because it is being obscured by the disk of dust grains that are orbiting around it. In the solar system, all the planets are orbiting in a single plane. In a new star being born, quite often there's typical as well. Everything's orbiting around, concentrated in a single plane, orbiting around that star. So we're looking edge on, and so the star is in the middle and we can't see it. But you can see that it's shining up and down and illuminating the other material around it. You can also say, well, might there be planets inside that little hamburger there, that dusty object? Probably yes. If we have to work a little harder to tell if there really are planets in there, but it's a pretty good guess because almost all stars have planets and quite a few. Now we know that. So come back in a little while, maybe 100,000 years, have another look. Maybe the dust will be all gone and maybe the planets will be easier to see. What else are we going to look at? Well, looking at the solar system, of course. Everything in the solar system from Mars on outwards can be seen. We can't see any closer than that because we can't point closer to the sun. Otherwise, the sun will get on the telescope. So anyway, two very interesting objects. Europa was observed and photographed by a visit. We paid a visit many years ago. And we saw that it has a surface covered with ice. And there are cracks in the ice, and once in a while water comes spitting up from the cracks in the ice blocks. So we've been watching those, and we want to see what are the chemical constituents of that water coming out. We're watching from here, and we're also planning a mission to go visit and fly through the plumes of water coming out to see could there be any organic molecules, anything that would tell you could that ocean under the ice be alive? So your guess is good as mine at this point about that. Here's another place we're going to visit. On the right-hand side is a surface map of Titan. Titan is unique among the solar system objects. It's the only place besides Earth that has lakes, rivers, rain, clouds, and weather of the same sort that we have. But it's a cryogenic version. It's cold. It's what, 40 or 50 Kelvin out there. So the lakes and rivers are made out of ethane and methane. And the clouds are made out of ethane and methane. And the topography is different on the equator than it is at the poles. Anyway, it's an interesting object. And it's interesting enough that we are sending another probe out there, including a lander, which will have its own little helicopter to fly around and examine the surface, and I'm not sure what else we're able to do on that one. Ideally, you'd say, can I bring home some pieces? But no, not yet. That's for future generations of space missions. Anyway, place to go look. And by the way, people want to know, and they often ask, are you sure that life elsewhere ought to be like life here? And how would I know? But this is a place where nature has done the experiment. They've got a lot of the materials available. They've got liquids, they've got water, solid water, and if there's any possibility that a very completely different environment could have life, we got to go look. So we've got a picture of Jupiter, of course. Even getting a picture of Jupiter is quite an accomplishment because it's spinning while you're trying to take a picture. So there's a software project for some of us that had to be accomplished to be able to piece together a picture of Jupiter while it's spinning and while the moons are moving and all the other things that are doing. But a few things to point out. The red spot's not red because we're using infrared light. We have to make up our colors in some way to be somewhat meaningful. Jupiter has a ring. It was not easy to see, but anyway, for a Webb telescope, it's pretty easy to see. Jupiter has auroras, north and south poles. It's really a fascinating place to study. So I guess most people noticed that we attacked an asteroid in the sense of dropping a very heavy metal object on it to see what would happen. and the impact was at very high speeds, so why do we care? Well, number one, you can see the debris coming out, which gives you a chance to analyze what's in the object. And number two, you get to see, well, how much is it going to move if you try to defend the Earth against an incoming asteroid? And so the interesting answer to that one is it moved about 5 times as much as we would have if it was just billiard ball collision. So where did that force come from? Well, it's the kinetic energy of the impact converted into heat, which causes the blast of debris to come out. And so the debris is like a little rocket engine pushing back on what's left of the asteroid. So we're just beginning to learn how to defend ourselves. And this is not the only thing to do, but there will be many, many more experiments to do so as to protect ourselves against that one. So, okay. Oh, I told you we were going to land on Titan. There's a picture of the lander up in the upper right corner. Little quadcopter. So by the way, how are you going to get enough power to fly a lander around when it's so cold and dark out there? We fly a thing called a radioisotope thermal generator. Plutonium-239 decays, produces heat. Heat can be converted into electricity. We've got batteries, store up the electricity in the batteries until you've got enough juice stored up to turn the rotors of the helicopter. And then you can fly for a while. So that's the secret method of flying around on Titan. So we, of course, as everybody wants us to look for life elsewhere on planets around other stars, and this is our method at the moment. We use transit spectroscopy. Small stars like M stars are about as big as planet Jupiter, and when a chance alignment, it's not so chancy, happens and a planet goes in front of its star, it blocks some starlight. You can say, well, that's interesting. I can now calculate the temperature of the object by how far it is from the star, which I get from calculations of the mass of the star and the orbital period and the brightness of the star. So now I want to know, well, does it have an atmosphere like Earth or not, or like any kind of atmosphere? And the answer so far is, after about 6 planets observed, is none of the small ones have an atmosphere that we can see, and all of the large ones have atmosphere because that's all they are. So Jupiter, Uranus, Neptune, those are all gas objects, and so yes, we can see them and they all have chemicals in them. So we know the technique works, and we are not too surprised that none of the little ones have an atmosphere that we can see, because we didn't expect it. But we have to try. So more coming. You'll probably hear people being disappointed that we haven't found Earth yet. But no, don't be too disappointed that we were not looking in the right place yet. The right place would be Earth's orbiting stars like the Sun. This is the one example of life that we have. So can you look there? Well, not with this tool. But an example of planets that do have chemistry. This particular one has been observed in 4 different ways with the observatory. And it has potassium, sodium, carbon monoxide, carbon dioxide, water, and sulfur dioxide, presumably more things in there. It's a big enough planet to have many things in it. Recently there was an announcement that a planet has dimethyl sulfide. And a lot of people said, maybe it's alive, because that molecule is made by life here. On the other hand, there's a lot of heavy breathing going on about that one. Probably not alive. In particular, if there were oxygen there, it would have oxidized that material. So now I want to talk a little bit about the future and what's coming next for us. And I'd like to say, well, you may think that we've accomplished a lot, and we have, but there's a lot coming. And Moore's law, I guess everybody's heard about. We were able to double the capabilities of little chips every 1.5 years. So how is that possible? It's because we got $1 trillion budget in the worldwide electronics business. So no problem getting the resources necessary to invent everything and discover everything. Some things are a little smaller in budget, such as the space business, but it's still big enough. And so there's another law that people haven't thought about very much, which is called Wright's law, that says if you learn how to, if you can sell a lot more product, eventually you'll find a way to make it cheaper. So you're seeing that in so many areas like electric cars and photocells these days, wind generators. So it's not very long ago when our friends were telling us we would never be able to afford to do the right thing for climate control. But they had not reckoned with if you build enough stuff, it gets cheaper. So suddenly, we've got a lot more rockets being launched all the time. And the communications people have discovered that they can put up satellites so we can get communications everywhere on planet Earth by way of satellite. And it's getting to be a problem, but it's also a source of immense amounts of money for engineering better rockets. So anyway, do not give up now. There's a lot more going to be possible and even affordable in the future. So what are things that are we doing now or that are coming soon? Here is a telescope that makes the Webb telescope look simple by comparison, but it's on the ground, so you can fix it. This is called the ALMA. How many people already know about the ALMA? Fair fraction of us. Anyway, it's a millimeter wave telescope, operates by collecting microwave signals from all of those antennas, converting them to go over fiber optic links to a central computer where they all combine in the computer to make an image. And the image on the left is one that's pretty exciting for some of us. It shows a new star with planets growing around it. You don't actually see the planets in this picture. What you see are the dust grains orbiting around the new star. And the story we tell is the dark gaps between the dust rings are places where planets are soaking up the dust. So maybe something like 9 planets in that little system. Come back in a little while. Maybe you'll be able to see the planets directly. Or maybe we need better equipment. We'll find out a way to see them sooner. I don't know what it'll take to see those planets, but something's in there. Something's going on. So that's beautiful. It's powerful. It's far more powerful than I ever imagined it could be. Anyway, totally amazing and already working. It has been made to work in partnership with other millimeter antennas around the world, and they're able to take a picture in a way of a black hole. How many people have already seen this picture of a black hole? A lot of you have. So you know the way they did it. They recorded the waveforms coming out of the telescopes on hard drives. And then with trucks, airplanes, and boats, they shipped them all to a center computer, and they combined them to make the image after the fact. So that's pretty cool. And they're very proud of themselves. We should be proud of their work because it's an immense technical accomplishment. But now, what do you do next? We could put another antenna into orbit around the Earth up at what we call geosynchronous altitude and combine it with the signals that we're getting from this collection, and we would be able to measure the spins of dozens of black holes. Because of the detailed shape of that little ring depends on the spin of the black hole. Black holes spin, which means they could change. They're actually dragging space around as they spin, which is a pretty weird phenomenon, but it's there, and we know it's happening. That ring isn't symmetrical because this black hole is spinning. So can we measure how black holes spin? Yes, we can. And we can do many. So my friends are working on this. So coming soon, or at least put it in this category of it's not impossible. And it's not even that hard. We could do this. Here's the kind of the opposite of a really big telescope. This is a really small telescope. Our friends up in British Columbia did this one. This is a collection of commercial telephoto lenses with pretty good cameras attached. And they took many, many copies of images of the same space on the sky so they could combine all the light to get a really good exposure. And they say that the galaxy on the right-hand side is 99.99% dark matter. Now, how would they know? Well, it's awfully faint, but it's being held together by something. and that something would be dark matter. It's got the gravity to hold it together. So another thing to point out, the only two men in this picture are the two old guys. So this is a transformation of our demographics of our profession. So anyway, many wonderful things about a very small object here. You don't always have to think giant. So I'll talk a little bit about the other things, discoveries that have been happening. These three gentlemen got their Nobel Prize for discovering, or should say, measuring for the first time gravitational waves using an optical interferometer. In this case, they've seen gravitational waves emanating from when two black holes get together, and also from when two neutron stars get together. So an astonishing capability which required extreme persistence and patience from the National Science Foundation, which funded the operation over decades. Ray Weiss on the left-hand side was also the head of the science team for the COBE satellite. So over 40 years of determination to get that thing to go. And it's not the end. They can now improve it and get many, many. And we will learn more. By the way, when you look at the heavy elements in the world, like gold, I've got some gold right here. Where did that come from? We think most of it comes from two neutron stars merging together. So when two neutron stars merge together in one of these giant collisions, a black hole is formed, and some of the extra gets spit back out into space to be recycled into future generations of stars, planets, and people. So here we are wearing some little pieces of neutron stars that collided. So pretty astonishing story we tell, and probably right, as far as I can tell. So you can also look at very, very, very long wavelength gravitational waves. Jocelyn Bell discovered them watching little traces come out on a chart recorder from ancient times, when that's what we had, looking at a pulsar. And she said, look at this, could be real. And her thesis advisor got his Nobel Prize for this. She was very polite about that. She knew her status was low as a graduate student, but she's been a wonderful spokesperson for the science, and now she's highly honored by our world, even though she did not get her Nobel Prize out of that. So what do we do with it? Among other things, we can now use those things as clocks to hunt for gravitational waves. So if all the pulsars in that half of the sky seem to suddenly be slower, and all the ones on that half of the sky are a little faster, we say maybe a gravitational wave came by. And so this team, the people that are working on this, are called Nanograv. They say they've got something. There's a signal there, and right now you can't identify a particular source. There's there's something going on. So the technique is working. So another Nobel Prize. Well, Jim Peebles on the left is the person who told us what we would find with practically every one of our cosmology experiments, and he's pretty good at that. The people on the right said, by the way, there are planets orbiting around other stars. When they went looking, people made fun of them, because of course there aren't any planets. You'll never find them. They did find planets by a method called radial velocity. So they watched the stars, and they could ever tell that some of the stars were coming toward us and going away from us with a sort of sinusoidal pattern. And barely possible at the time, but they said they are there. So they got their Nobel Prize for the first discovery of planets orbiting other stars very, very clearly. They started a gold rush. People said, we'll do that too. And so now we know many other things have been done. We now know that most stars have planets, and most have many planets, and about 20% have planets about the right size and temperature to be like Earth. So are we alone? Don't know. But there are places you could potentially live if you could get there, which you can't. Sorry. So, okay. So talk a little bit about adaptive optics. Adaptive optics is a method that we have to correct for the turbulence of the Earth's atmosphere. And the Earth's atmosphere is quite turbulent. It means when you go get a telescope about this big that you can afford for yourself on your personal budget, maybe, and you see a star, it's not perfectly sharp because of the atmospheric turbulence. And if you get a bigger telescope, like what we have upstairs, the image is not any sharper. It's just a lot brighter. So you say, can I do anything about that? And it was proposed in 1953 that yes, you could, if you could measure the variant turbulence of the Earth's atmosphere and compensate for it with what's called an adaptive mirror in this picture. So the answer is yes. If you've got something to focus on, and if you can tell if you've done it right, then yes, indeed, you can get a sharper picture. So it's called adaptive optics. We have technology to do this. Currently, the thing that we use to focus on is we send up laser beams into the upper atmosphere and then make the upper atmosphere fluoresce because there's sodium atoms up there. So that we have sort of artificial stars, but they're not very sharp. So we do the best we can. But it works. On the right-hand side, by the way, I show you that if you go to see your eye doctor, they have a technology like this. It was immediately understood that your eye doctor needs to see the back of your eyeball better. And your eye is not a very good lens all the time. And besides, you're constantly refocusing to look at things. So can we possibly build something that does the same thing for your eye doctor? And the answer is yes. So they can see the back of your eyeball a lot better than ever before. And not only that, they can measure what to do if you want better eyesight. If you're a football player, it's your professional motivation to have much, much better eyesight. And so you can get this done. I understand the professional football players do get this done. They can have surgery on your eye to get 20/10 eyesight. So who knew that astronomers and football players needed the same thing? So I tell you that because it's going to come back. Now everybody wants us to find more planets. So here's one that's up there working. It's a relatively small collection of instruments that take pictures of the sky all the time to look for when a planet goes in front of a star. And they're telling us many, many, many. And the good thing about these, when they discover them, is they are as close to Earth as possible, so we can follow them up very well. So when this was conceived and posted, I said, gee, I wish I'd thought of that, because it was so obvious. But it's not so obvious how to really do it. But anyway, they did it, and it's working. So what else are we doing? Here's a European telescope that was just launched a few months ago on July 1st. It is looking for dark matter and dark energy. How do you do that when you can't see them? Well, you take pictures of the galaxies and see is anything funny about them. So the answer is yes. You can deduce the existence of dark matter and dark energy if you get enough pictures of galaxies. So the telescope is only this big, but it's enough to make progress. The United States and others are building this telescope. It's called named Vera Rubin Observatory. Congress said, please build it and please name it after Vera Rubin. She was an astronomer at the Carnegie Department of Terrestrial Magnetism in Washington, D.C., and is one of the people we would thank, if we could, because she's passed away now, for discovering dark matter. She showed that galaxies spin in a way that can only be explained if they have dark matter. Nobody knows what dark matter is, but we got a proof that it's there. So this telescope is going to survey the entire sky every 3 nights from its perspective, and every night 10 million things are expected to be changed compared to last time they looked. So we're going to need pretty good computers to track down which one of those things are worthy of following up with other observatories. But when 10 million things happen every night, you're going to be busy. I like to say, well, we don't have enough graduate students to do that. We don't even have enough artificial intelligence yet to do this, because processing this data is right at the limits of what can be done with Moore's law and all the growth in computers. Anyway, it's coming. Thank you, Vera. We are going to launch this telescope named after another astronomer, Nancy Grace Roman, who was the head astronomer at NASA headquarters for a very long time, and was in charge while we built a whole long series of wonderful telescopes, including the Hubble. Anyway, this telescope is the size of the Hubble. Sorry, this telescope is the same size as the Hubble, but can take 100 times as much sky in one bite. And We'll be surveying the sky again to look for dark matter, dark energy, and rare events, and even hunting for planets. So it's got a device called a coronagraph, which will make our next best attempt to see planets around other stars. So now coming back to what's on the ground, I told you about dark matter, about adaptive optics. We have 3 giant telescopes that people are building or want to build. The European one is the biggest, 39 meters across. Can you imagine 39 meters? It's almost the width of a football field. And so they have something like 1,000 mirrors that they're taking up to the mountain. They will assemble it into a giant, more or less circular mirror. And it will have the not only brighter images, but also they will be able to do that adaptive optics that I was telling you about to get sharper images of everything. The 2 US-led ones on the left are, neither of them has enough money to go quite yet, but people are working anyway. The one in the upper left, the Giant Magellan Telescope, they've just started their 7th mirror. So they're building the mirrors even if they don't have enough money yet to finish the job. So they're hoping it will get to go. So we are building things that are going to be totally spectacular on the ground as well. And they will use that adaptive optics. So now I want to talk a little bit about a couple of projects I've been working on. We said, well, how about that adaptive optics? We need something to focus on. Can I shine something down from space onto the telescope on the ground so I can see better? And the answer is yes. I'm going to put a laser beam shining down from the space onto my telescope. Then I can focus on it. So we figured out how to do this. We could do this if somebody said go. We know what it takes. And you can buy almost all the parts. So we're still waiting for a way to say, can we have our turn, please? Which is a long process. But anyway, I think it's a good technical idea, and it might yet happen. Here's my wildest idea. If you wanted to see planets around another star, you could say, can I block out the starlight with something so I could see? The challenge here is the sun is 10 billion times as bright as the Earth, so I need to block something out really well. So my sketch on the left says, let me put up a star shade. Cast a shadow across 170,000 kilometers of space onto that European telescope that I was showing you, and then we'd be able to take that picture on the right-hand side in 1 minute. And I think that is so cool. So we don't know how to build it, so ask again in a while. Maybe we'll figure it out. Well, we do know how to build it. We just don't want to pay that much money. We need a better way. So if you could do it, you could even see that there's oxygen and water in the atmosphere of another Earth. So I'm going to just show you that I have the picture. Maybe talk about it more later if people want. But we know that you could tell. If there was an Earth that was really like Earth, we would know. So what's NASA going to do next? We have a process called the Decadal Survey. Every 10 years, the National Academy of Sciences writes a book for us that's saying, this is what we think you all ought to do. Because this is the coolest projects, there's the best science to do. And they wrote a report this year that said, or a few years ago, they said, we recommend a telescope as big as the Webb, but capable of seeing little planets like Earth orbiting around stars like the Sun. And okay, NASA would like to do that. When the book says do that, that's what we like to do. The Congress will probably fund it when we're ready. We also evaluated in this report 2 others, an X-ray observatory and a far infrared observatory. And I think it's clear that there's science there that can't be done any other way, but can't do it now, can't do them all at the same time. So the one that goes first is the one that goes first that's got the priority, but I think the other 2 will happen later. Basically this says, we've got a century's worth of work in front of us. If you're an astronomer, you're not going to run out of things to do. So now I just want to wave my arms a little more vigorously and say there are things you would never even thought of that are useful for astronomy. Atoms can be split like light waves. Atoms can be divided coherently into 2 pieces and sent them into different paths and recombined. And you say, why would you want to do that? Because you can measure gravity with them. And so We can tell whether the Earth's gravitational field is changing with time, and we can tell if gravitational waves are coming by using this technology. I'm just not showing you how to do it in detail, I'm just showing you that it can be done. So, not impossible. You can focus X-rays. We've got a small X-ray satellite up there that's actually working currently. Was just launched 2 months ago, and it's working. So we're very proud of that one. We have built a telescope in Antarctica to look for neutrinos. Neutrinos come up through the Earth, make a flash in the ice. We see the flash, we calculate what it came from, and sometimes we can trace the neutrino back to an object. So this is a huge investment, and it's incredibly difficult. They've got deep holes full of photomultiplier tubes. So, amazing thing that they did. Anyway, so what do you want to do next? I don't know, but there's plenty already coming. So thanks for the invitation to speak, and I'm happy for questions.